lesson where I'll be answering questions on the topic of electromagnetic induction. Question 1 says the following diagram shows a magnet attached to a spring and set to oscillate up and down above a coil connected in a circuit. Which statement is correct about the arrangement in the diagram? Statement A says alternating current will flow in the circuit. This is definitely correct. Let me explain. Okay. From the information provided in the question, we are told that the magnet is oscillating up and down. So, because of this continuous oscillation of the magnet is creating a changing magnetic field through the coil. So, it is making the coil to experience a change in magnetic field. Following the principle of electromagnetic induction, if there is a change in magnetic field through a coil, then an EMF is produced, and that EMF in turn causes an induced current to be produced. To be specific, the type of current that is produced is alternating current. Alternating current implies that the direction of the flow of current changes periodically. So, in this case, alternating current will flow in the circuit. For clarity's sake, let me go over the rest of the options. Option B says direct current will flow in the circuit. No, this isn't correct because it's not direct current that flows in the circuit, but rather alternating current. So statement B is incorrect. Statement C says the magnet will be attracted to the coil. This statement is not correct because it is not fully developed. Okay, let me explain. For the magnet to be attracted to the coil, um, it means that the magnet was withdrawn. So when the magnet is withdrawn, that's when the coil creates a pole that would attract the magnet. However, the statement C does not seem to incorporate this idea, so we regard it as being incorrect. Okay, statement D says the magnet will be repelled by the coil. Again, this statement is not fully developed because the only scenario in which the magnet is repelled by the coil is when the magnet is introduced into the coil. So when the magnet tries to get closer to the coil, that's when the coil repels the magnet. That's the only case. So statement D is also not fully developed, so we regard it as being wrong. Therefore, here our ultimate answer is option A. Alright, question 2. The following diagram shows a step down transformer. Given that this transformer is 100% efficient, which of the following is the correct pair of voltage and current in the secondary coil? Okay. The statement 100% efficient means that there is no power loss. Therefore, it is safe to assume that power at the primary coil is equal to the power at the secondary coil. Okay, so in this case, let me first find the power at the primary coil. Remember, power is equal to voltage times current. The voltage I'm given is 240. The current is 0.2. So if I do my calculation here, I'm getting a value of 48 watts, right? That's a value I'm getting. So in this case, I will have to find a pair that will give me 48 watts to have my answer here. Okay. Option A, voltage 12 and current 2. If I calculate power using this, I'll have a value of 24, which isn't correct. Option B, 8, voltage 8 and current 3. If I calculate power here, I'll have a value of right, let me put it. So here I'm having a value of 24. Okay, and also here I'm having a value of 24. Remember, power is VI, so that's what I'm just doing. Just multiplying the voltage and the current. And here I'm having a value of 48. And here I'm having a value of should be 36. So in this case, the one that gives me the power at the secondary coil to be 48 is option C. So I'll go with option C. Right. Question 3. A DC generator can also be okay. In this case, it is ideal that we know that both a DC generator and a DC motor have the same setup. So here, a DC generator can also be a DC motor. They basically are created in the same way and they have the same structure. What differs, the only thing that differs is their usage. A DC generator is used to convert kinetic energy into electrical energy, whereas a DC motor is used to convert electrical energy to kinetic energy. That's the only difference. Otherwise, the setup and everything and the way they are created is exactly the same. Therefore, a DC generator can also be a DC motor. It is also true that a AC generator can also be an AC motor. Okay. So in this case, we're going with option C. Question 4. The following diagram shows the permanent magnet being slowly introduced into the coil of wire, which is connected to a sensitive galvanometer. Right. As the magnet is slowly withdrawn from the coil, what are the polarities of P and Q? Okay. So by withdrawn means that the magnet is moved in this direction, right? So following Lenz's law, if we try to move the magnet away, then the end of the pole here at P will be north. So it will be north because it would want to attract the magnet, therefore preventing the action that which we are doing. So NP will create a north pole and NQ will create a south pole. So P is north, therefore option A is correct here. Okay. Question 5. Which of the following devices does not use the motor effect in its operation? Remember, motor effect is the principle that is used in designing motors. Okay. I established a fact to say that motors convert electrical energy to kinetic energy. So in this case, if we've been as simple as possible, the question is just trying to say which device here converts electrical energy to kinetic energy. So a DVD player does convert electrical energy to kinetic energy. An electric fan as well does the same. A starter motor also does the same. The only one which does not do this is the microwave oven. So here my answer is option C. Question 6. The following diagram shows a step-down transformer. Okay. How many turns are in the secondary coil and what is the size of the current in the primary coil, assuming the transformer is 100% efficient? Okay. So, step 1, let us first determine the number of turns in the secondary coil. Okay. We'll use the formula that says N S over VA should be right. Sorry on that. Should be NP, yeah, is equal to VS over VP. So in this case, we want to find the number of turns in the secondary coil. So we'll basically make it the subject. So NS is equal to, we'll cross multiply there. So we have number of turns in the primary coil, remember, is 2000 times the voltage in the secondary coil, which is 12 volts, over the voltage in the primary coil, which is 240. If I do my calculation there, I'm having number of turns in the secondary coil to be 100. Okay. Remember, this question has two parts. The next part now is requiring me to find the current in the primary coil. So for current, we use the formula that says IS. Okay, let me just try and derive it first. Remember in that question where I said, when they say the transformer is 100% efficient, it means that there is no power loss. Therefore, power in the primary core is equal to the power in the secondary core. And power, the formula of power is simply VI, right? So we have that I1, V1, right, let me put in P, is equal to IS and Vs, because there is no loss in power. Therefore, this is the formula that I will use. Okay. I said IS Vs is equal to Vp Ip. Okay. So we want Ip here. So Ip will be equal to IS. IS is the current in the primary coil, I mean the secondary coil, which is 4 amps, times Vs, which is 12, over the voltage, which is 240. So in doing this, 4 times 12 divided, I'm getting a value of current to be 0.2 amps. Okay, so my number of turns is 100 and my current is 0.2. So let me find this pair, and this is option A. Okay. Question 7. Elena investigates electromagnetic induction. She has a bar magnet and a coil of wire that is connected to a sensitive ammeter. Which movement does not cause a reading on the ammeter? Right. Okay. It is essential that we understand that for electromagnetic induction, the only way in which the ammeter can register a reading is when this coil here experiences a change in magnetic field. When the coil does not experience a change in magnetic field, then the ammeter can never register a reading. Therefore, we are considering the factor that does not cause the coil to experience a change in magnetic field in this question. Okay. Right. Okay. Let's check option A. Option A says both the magnet and the coil, I think they should be moved here, move towards each other at the same time. Alright, let's try to imagine this. So both the coil and magnet move towards each other at the same time. So maybe the coil is going in that direction and the magnet in that direction. If this occurs, if this transpires, then surely the coil will experience a change in magnetic field, and a change in magnetic field will cause the ammeter to register a reading. In this case, we want which one does not. So option A is incorrect. Option B. Right. Option B. Both the magnet and the coil to the left at same speed. Okay. If we take the magnet and the coil to the left at the same speed, then this coil will not experience any change in magnetic field. And because the coil is not experiencing a change in magnetic field, therefore the ammeter will not register any reading at all. Thus here my answer is A. Okay. I mean my answer is B, sorry. Yeah. Question 8. The coil of a simple motor lies between the poles of a magnet. When current is introduced in the coil, it rotates on its axis. Which of the following decreases the frequency of rotation of the coil? Okay, let me try to imagine this scenario. So this means something like this, right? So it lies between the poles of a magnet. So then it should be something like that, right? Okay. Okay. So The factors that which the frequency of rotation of this coil depend, the factors that which it depends upon. Number one is current. It is current. Number two, it is the number of turns. Number of turns. Number three, it is the strength of the magnet. Okay. Alright. So these are the three factors which the frequency of rotation depends upon. Okay. Right. So we want the factor that decreases the frequency of rotation. Option A says increasing the number of turns in the coil. If we increase the number of turns in the coil, then it means that we will increase the length of the conductor. And if we increase the length of the conductor, it means that the conductor will cut across the magnetic field more frequently, and thus it will increase the frequency of rotation and not decrease it. Therefore, option A is incorrect because it results in an increase in the frequency of rotation. We want a factor that decreases the frequency of rotation. Option B says reversing the current being used. If we reverse the direction of the current being used, there is no impact on the frequency of rotation here. Therefore, option B is also incorrect. Option C says using a high voltage supply. Remember, voltage is equal to I times R. If resistance is constant here, an increase in voltage will have an increase in current. Okay. And remember, I also emphasized to say that the frequency of rotation depends on the current, in that the higher the current, the more frequent the rotation is. So in this case, if we use a high voltage, it means that we use a high current, and a high current will increase the frequency of rotation. So therefore, option C is also incorrect here. Then option D says using a low voltage supply. If we use low voltage, this means that the current will also decrease, and if the current decreases, then the frequency of rotation also decreases. So the one that decreases the frequency of rotation is actually option D. Okay. Question 9. The primary coil of a transformer has 200 turns and it is connected to an AC power supply of 25 volts. A voltmeter connected to the secondary coil reads 50 volts. Right. Find the number of turns on the secondary coil. Alright. So we'll simply use this simple formula. Ns over Np is equal to Vs over Vp. So we want the number of turns in the secondary coil. Okay. So Vs will equal to, will multiply Ns times Vp, right? Ns meaning number of turns in the, right, sorry on that. I didn't make it the subject. Okay, let me start over. Alright. I said Ns over Np, right, is equal to Vs over Vp. So we want Ns. So we'll cross multiply Np and Vs. Number of turns in the primary coil is 200. So it is 200 there. And the voltage in the secondary coil is 50 over the voltage in the primary coil, which is 25. So 25 in there will give me 2, and in total I'm having the value of 400 turns. Thus the number of turns in the secondary coil is equivalent to 400. So option D. Alright, question 10. The diagram below shows a brass rod and an iron rod beside each other at the bottom of a rectangular coil. What happens when a direct current passes through the rectangular coil? So in this case, EZ expected us to know that iron Iron is one of the few examples of the substances that can be able to be magnetized. Okay, and brass cannot be magnetized, meaning it cannot attain magnetic properties. It's only the iron that can attain the magnetic properties. So in this case, the iron will be magnetized when direct current flows through it, and the brass will not be magnetized when direct current flows through it. Now, other examples of substances that can be magnetized are cobalt, nickel, as well as steel. So, in our syllabus, these are the common examples of substances that can be able to be magnetized. Alright, so which one has this? Only the iron rod is magnetized. So, option C here. On that note, let me end this first part of electromagnetic induction.